Okay, so let's start by learning about the first principle in the solid design principle, and also maybe the most commonly used of the bunch, the S, which stands for the single responsibility principle. This principle states that a class should only have one reason to change or one and only one responsibility. That means that a class should do one job and do it well. Why does it matter? Well, if the class has only one responsibility, that means it's easier to maintain and update. Smaller classes are well defined and simple to understand and test. But the single responsibility principle can also apply to methods or functions themselves, not necessarily the entire class. So, with that in mind, let's take a hands-on example of how we can implement this. I set up a simple example to demonstrate this. I made it as straightforward as possible. We don't need a very complicated example to illustrate this. Suppose we have a form to add clients to our database. Here in the store function of my client controller, we have all the logic needed to store the client's data. First, we validate the incoming data. Then, if that passes, we store the client data in the database. After that, for example, we send an email notification to that client indicating that their account has been created and return a success message to the front end. As you can see here, the store method is now responsible for too many things besides just storing data in the database. It is also responsible for validating the data and sending the email. But under the single responsibility principle, this method should only do one thing, which is creating a record in the database. So let's fix this to conform more to the single responsibility principle. First, let's refactor the validation logic. So instead of keeping your validation logic here, you can put it in its own dedicated class. To do that, open the terminal and create a form request class. So for example, create client request. Inside this file, we'll move our validation logic here. Let's go back to the controller, copy all of the validation logic, and move it into the array inside the newly created class. Okay, and don't forget to set this to true to authorize the current user to make this request. Now, let's return to the controller. We can safely remove all of the validation logic from the store method. Then, replace the generic request parameter in the store method with the class we just created. Create client request. Next, let's update this part to use just request. And we also need to convert this into an array, since the create method accepts an array. Additionally, update this to use the email property directly instead of referring to it as an array key. Let's quickly remove this numbering. Okay. The next thing we'll tackle is this mail notification right here. Again, according to the single responsibility principle, it doesn't belong in the store method. Now you could put this in a service class, but to keep things simpler, let's just move it to a trait. In the app directory, I'll create a new directory called concerns. Inside this directory, I'll create a new file called, let's say, clientmailnotifier.php. Okay, let's create a simple trait here. Well, as you can see, GitHub Copilot seems to know what I'm going to do, so let's simply accept its suggestion. Next, let's import all the necessary classes. Let's declare this as a string. Now that we have this trait, our mail notifier is a bit more reusable instead of being confined to the store method. By the way, this is the email markdown template that we will send. It just contains a very simple message. Let's go back to the client controller and make use of this trait. At the top of the file, I'll include a trait. Make sure it's properly imported. Now, instead of directly sending the email in the store method, we'll delegate that responsibility to the client mail notifier. Let's say this, notify client, and provide the email address where you want to send the notification. Now we're almost finished. As you can see, the store method is significantly cleaner and improved. It's now solely responsible for saving the client's data to the database and no longer has to handle the validation logic. Now, you might say, sure, we have moved the validation logic to its own class, but the email notification is still being called from here. The store method is still responsible for sending the email. Well, while it might seem that way, that's not actually the case. The store method is not the one sending the email. Instead, we outsource that responsibility to the trait that we created. The store method is merely calling the trait and instructing the notifier to send the confirmation email to the client. It doesn't need to know what's happening inside the notify client function. So it's like saying, hey, Mr. Notify Client function, please send a confirmation email to the client on my behalf. Now you could also create some sort of a responder class to make the response function more reusable. But I am confident that you get the idea here. Okay, everything looks good. We've implemented the client validation logic, so it's time to test this out. But before we do that, I'm going to run a queue worker since I've placed the email notification into the queue for background processing. So it's just a habit of mine. Okay, the queue worker is running, so let's test this out. I'll open the network tab to check the request. If I hit the submit button without providing any details, and look at that, our validation logic is still working. As you can see, here are the validation error messages. Now let's try filling out the form fields. As you can see, the request succeeds. So let's check the queue logs. And yes, the queue worker picked that up and sent the email. Let's quickly check the email. I'm using MailPit as my email testing tool. And here it is. Cool, it works. I just want to quickly mention that this is a hypothetical example. Of course, in the real world scenario, you might want to wrap this in a try-catch block to handle any exceptions that might occur. I'll leave that part for now, but you get the point. Okay, that wraps up the single responsibility principle. So let's move on to the O in solid, which stands for the open and close principle. Now let's talk about the open and close principle in solid. By definition, the open and close principle states that classes, modules, or functions should be open for extension but closed for modification. Why does this matter? This principle promotes the ability to add new features, behaviors, or implementations to an existing class or function without altering the existing code. So this helps reduce the risk of introducing bugs or breaking existing functionality when adding new features. To demonstrate this more clearly, so let me show you a simple practical example. Suppose we have an app that accepts payments. Here I have a simple pay button. Now imagine your app uses Stripe to process online payments, and that's the payment processor you've implemented in this case. In the payment controller, we have a charge function where you've written the logic to accept payments using Stripe. So I'm not going to write out the entire code to handle the payments, but for the sake of example, let's just imagine that this is where you've implemented the payment processing logic. If we turn to the browser and test this out, I'm going to open the network tab to inspect the outgoing request. Hit the pay button, and let's inspect the request. Sure enough, we see the message, payment processed by Stripe. Okay, it's working. Now, I want you to think about this. This code, for example, is specifically designed to handle payments using Stripe. But what if in the future, your company or your boss, for example, decides to add another payment processor to the app? Let's say Paddle or PayPal. But the current implementation is tailored for Stripe. To accommodate this change, I've seen developers handle it by adding a quick check to determine which payment processor the app needs to use, for example. Alternatively, they might also write the implementation in a separate function. For instance, creating a new function like paddle charge. However, this approach makes the code more vulnerable to breakage or bugs. The class can become very large and increasingly difficult to maintain, making it cumbersome to add more payment processors in the future. This practice violates the open and close principle because the function responsible for processing payments must be modified whenever a new payment processor is added. This means it is not closed for modification, nor it is properly open for extension. Remember, the open and close principle states that classes, functions, or other entities should be open for extension but closed for modification. With this current implementation, adding a new payment processor requires extensive modification, which goes against the principle. Now, to fix this problem and make our code more extensible and maintainable, we need to separate the extensible behavior of our code behind an interface. And when I say interface, I don't mean a user interface that you see in the browser. I'm referring to the PHP interface. So let's do that right now. So I am going to create a new interface under the contracts directory inside the app directory. Let's name it paymentprocessor.php. Okay, so first, let's set up the namespace. Then I'll define the interface here by saying interface payment processor. This is often referred to as a contract. So it's a guideline or set of rules that all classes implementing this behavior must follow or adhere to. For example, if we define a pay function inside this interface that accepts the amount to be paid, every class implementing this contract will be required to have a pay function with the same signature. If a class fails to implement the pay function, it will result in an error. Now, let's make use of this interface. We will create a new service class for the current payment processor we have, which is Stripe. Under the app directory, we will create a new directory called services. Inside the services directory, let's create a new service called Stripe payment processor.php. Okay, and don't forget the namespace. This class will implement the payment processor contract. Implements payment processor. Now, as you can see, the editor will show us an error saying that we need to implement a method called pay. As I mentioned earlier, we need to adhere to this contract, which means implementing the method stubs defined in our interface. Okay, so let's add this here. And it will accept the amount. Now inside this method is where you'll put the logic required to process payments using Stripe. So for now, I'm just going to return true, as this is only an example. Now that we have established this, the next thing we need to do is to create a class to actually process the payments. I'm going to create a new service class called paymentservice.php. It will have a process function, which is where we will actually handle the payment processing. We need to initialize the payment processor here. So let's declare this as a protected property so that only this class and its subclasses can directly access it. Now in the constructor method, let's initialize the payment processor. After initializing it, we can now make use of it inside the process function. We can return the payment processor, and as you can see, there's the pay function that we declared in our interface. We will supply the amount as the parameter here. So let me add a comment. So this function delegates the actual payment task to whichever payment processor is passed in. Okay, this is complete. Let's go back to the payment controller to begin using the service classes we just created. I'll delete this. Well, actually before that, let's create a simple config file to determine which payment processor to use. In the config directory, let's say that we have a payment.php config file. This config file will include a payment processor option, and we'll set this in the .env file. The default will be Stripe for now. Later, we will add another payment processor, and you'll see how easy it is to swap implementations this way. Back to the payment controller. Instead of using an if statement, let's try a match expression. The match expression will accept an argument to determine the current payment processor being used. as declared in our config file. If the payment processor is Stripe, we will use the Stripe Payment Processor Service class. Okay, so next, let's initialize the payment service, which will process the payment using whatever payment processor is specified. Later, we will add another one. Finally, let's process the payment. For example, payment successful will be equal to the payment service, and then we'll call the process function, passing the amount to be charged, and of course, we'll update the reference from Stripe payment to payment successful. Okay, I got an error here. Okay, I forgot to close the match expression. Okay, all set. Now let's try it out. Go back to the browser and I'll open the network tab. When I hit pay, as you can see, it still works. Payment processed by Stripe. Now here's the thing. What about if we need to implement a new payment processor? Suppose your company or boss tells you that we also need to support Paddle to accept payments. In this case, it's going to be easier. All you need to do is simply create a new class. Let's name it Paddle Payment Processor.php. To save some time, I'll just copy everything from Stripe Payment Processor, paste it here, and change the class name to Paddle Payment Processor. Of course, inside the pay function, you'll need to write the logic for processing payments using Paddle. Then, in the payment controller, you simply add Paddle as an option in the match expression. And that's all you need to do to add a new payment processor. So let's try this out. In the .env file, let's change the payment processor from Stripe to Paddle. I'll also change the message so we know which one's being used. Okay, so let's test this again. Back in the browser. Oh, I got an error. Unhandled match case. Okay, let me check this. I accidentally added a dot here. Let's fix that and try it again. Hit pay. And as you can see, the payment is now handled by Paddle. Let's switch back to Stripe. Try it again. And it works. Now I hope you can see the benefits that the open and close principle brings. First, our classes are now focused on their own responsibilities. So when you need to add a different payment processor, you don't even need to modify any of the existing payment processor classes. The only thing that you need to do is to create a new service class. For example, if you need to support PayPal, you simply create a new class, implement the payment processor contract as we did with Stripe and Paddle, and add that option in the match expression. The process function in the payment service class will take care of the rest. You also don't need to change anything in the payment service class. As you can see, the process function that executes the payment process doesn't need to be modified anymore. This implementation is now more adherent to the open and close principle, since it's very easy to extend the functionality of our app without modifying the other classes or functions that are already working well. I hope this example is sufficient to demonstrate the benefits of the open and close principle. Next, let's turn our attention to the L in SOLID, which stands for the Liskov substitution principle. Okay, so let's turn our attention to the Liskov substitution principle. It may sound intimidating at first, but once you understand the principle, it's actually not that complicated. By the way, Liskov is the name of the person who introduced this principle, Barbara Liskov. The Liskov substitution principle, or LSP, states that objects of a superclass or an interface should be replaceable with objects of any of its subclasses without breaking the program's functionality or correctness. In other words, a subclass must adhere to the contract of its superclass in such a way that it can be used interchangeably. And of course, the best way I think to explain it further is again to show a simple but practical example. And later on, I will also show you what might happen if we don't follow the LSP. I set up a simple example here to demonstrate this principle. So for simplicity, I'll put everything in a single file so we don't have to switch between multiple files. Imagine that in this section, we are going to display the user's information fetched from an external API. Let's say a social media API, for example. In our controller, let's create an interface that our social media class can implement. Let's call the interface userFetcherAPI, and we'll define a function in the interface, but let's simplify this to just fetch. Next, we will create an example API class, such as Twitter API, for example, which implements the userFetcherAPI contract. Remember, when implementing a contract, we need to adhere to it by implementing its defined functions. So we'll declare the fetch function here. Under this method, we'll include all the logic needed to fetch the user's data from a specific API. Okay, so let's make an example API request. I'll use the HTTP facade and grab some data from a website called jasonfakery.com. So if we go to the user's page, we can use some API endpoints here to fetch some test data. I'll scroll to the bottom and grab this endpoint to fetch a random user for our example. I'll paste the endpoint here and return some data from it. Okay, to keep things simple, I'll output a few properties from that endpoint. So think of this as fetching user information from the Twitter API. Now, in our controller, we can instantiate the Twitter API class to fetch some data. We'll say data equals new Twitter API. Then call the fetch function from our contract. And finally, return the data as JSON. In the web route, I've already set up the route here, as you can see. If I go to the component where we render the information, it's simply making an endpoint call. It's very straightforward. Okay, now in the browser, let's test this. I'll open the network tab, refresh the page, and there's the data coming from the API. It's properly displayed here. Okay, next, let's say there's an additional requirement for this app that should fetch users' information from another source. So for example, your boss wants to add support for GitHub's API to fetch user data. We learned from the previous lesson that we can simply create a new class for this specific API. So let's go back to the controller. So to simplify, we'll borrow the code from the Twitter API class, rename it to GitHub API. Adhere to the contract by implementing the required function, and then write the logic needed to fetch data from GitHub, for example. Once that is done, all we need to do is swap out Twitter API for GitHub API. Okay, that is simple enough. Let's test this, refresh the page, and sure enough, we got the response back. This kind of implementation follows the Liskov substitution principle, because we can easily swap out the subclasses without rewriting anything from the original class or making changes to the front end to display the user's details. Now, here's the thing. What happens if we violate the Liskov substitution principle? Let's intentionally violate this principle to fully understand its importance. Remember, the Liskov substitution principle states that subclasses should be completely interchangeable or substitutable without breaking the functionality of the program. In our GitHub API class, instead of returning an associative array, let's try changing it to return just a string, for example. Okay, we'll return only the user's name. So now the GitHub API's fetch function is returning a string instead of an array like in the Twitter API class. Let's go back to the browser and see what happens. If I refresh the page, there are no exceptions, okay? The request still succeeds with a status 200 and returns the data. However, look at our component here. Nothing is displayed. This happens because our component is expecting an object, but we return a string instead. This is a clear violation of the Liskov substitution principle, because the Twitter API and the GitHub API class are no longer interchangeable due to their different return types. One returns an array, while the other returns a string. As a result, this leads to an unexpected behavior like this. You might think it's easy to fix by adding a quick check, for example, an if-else statement to determine whether the return type is a string or something else. However, this should serve as a hint. When you encounter code that requires such type checking to handle inconsistencies, it's a sign that the Liskov substitution principle might be violated. Okay, so let's go back to the controller. As you can see, the GitHub API is returning a string, while the Twitter API is returning an array. Both of these classes have different return signatures. So let's just add a comment here. This violates the LSP. To fix this issue, always remember that subclasses must have the exact same return types and method signatures. Simply matching the method signature isn't enough if a subclass changes its intended behavior or adds constraints that breaks the code's expectations. You must ensure that substituting one subclass for another never causes unexpected behavior like we saw earlier. This principle is widely used in the Laravel framework itself. For example, if you look at the mail.php config file, Laravel supports many email drivers such as SMTP, Mailgun, Resend, and others. If you decide one day to switch email providers, all you need to do is to go to the .env file and update some or all of the mail variables here to establish connection to the new email provider. And that's it. You don't have to change a single line of code in your mailable classes or email templates. It will just work. The same concept applies to the database drivers. Laravel supports several database drivers like SQLite, MySQL, MariaDB, PostgreSQL, etc. To switch databases, all you need to do is specify the new database driver and credentials in the .env file. Assuming the database driver is properly installed and running, everything will continue to work seamlessly. Okay, so that is a very basic example of the Liskov substitution principle. Up next is the I in Solid, interface segregation. Okay, now we're on the fourth principle of Solid. The interface segregation principle, or ISP, states that no client should be forced to depend on methods it does not use. So in simpler terms, it means we should split larger interfaces into smaller, more specific ones so classes only implement the functionality they actually need. When an interface contains a large number of methods, any class implementing that interface is forced to include methods it may never actually use. This may lead to unnecessary dependencies and code bloat. You might end up wasting a lot of time maintaining functions unrelated to the class's actual responsibility. By splitting these fat interfaces into smaller, more targeted ones, each class only implements what it truly needs. This approach not only keeps your code cleaner, but also adheres to the single responsibility principle by preventing classes from taking on too many responsibilities. Additionally, keeping interfaces small and focused promotes looser coupling. When an interface has fewer methods, changes made to that interface or its concrete implementations are less likely to cascade and cause issues in other parts of the system. This modular approach allows each component to evolve independently, making the codebase more resilient to changes and easier to maintain over time. Okay, so here in our example, just like in the last lesson, I'll put all the classes in the same file for simplicity. Imagine we're building a feature in our app for managing users, along with some basic functionality for assigning roles and permissions to determine what users can do within the app based on their roles, which is a very common feature on many applications. Here in the user management interface, we have a couple of methods here for fetching users and some for granting and revoking specific permissions. So let's implement this interface and build the features. Just like in the previous lectures, we need to adhere to this contract by implementing all the functions defined in the interface, right? We've done this before, so let's add all the defined functions from the contract into the class. One by one, we'll provide simple logic. For example, for the fetch user by ID method, let's return the user with a specified ID. For the fetch all users method, let's paginate the results by 10. Okay, nothing complicated so far. Now for the last two methods. These methods are somewhat related to granting permissions to the user. So you might argue that they have nothing to do with the user's controller. This means we are violating the single responsibility principle here. However, because of the contract, we are required to implement these methods. Otherwise, we will receive an error. Since these two functions don't belong in this controller, you might be tempted to simply return null to avoid the issue. Okay, so for example, if I comment these methods out, you'll see that it throws an error saying we need to implement those functions from the contract. So we have no choice but to include those functions even if they don't belong here. Let's uncomment these for now. This implementation is a clear violation of the interface segregation principle, or ISP. It violates ISP because this class is forced to implement one or more functions that it doesn't actually need. But currently, we have no choice but to use these functions since they are declared in the contract. So how can we solve this problem? Well, as the name of this principle suggests, we need to segregate related functions into a separate interface. Additionally, if you think about it, this implementation not only violates the interface segregation principle, but also the single responsibility principle. Looking closely, the user controller class is taking on multiple responsibilities instead of focusing solely on functions related to users. By including methods for granting and revoking permissions, it's stepping outside its intended role. Let's fix this by creating a new interface dedicated to roles and permissions. So let's call it User Permission Manager Interface. The name might be a bit long, but that's fine as long as it's clear and easy to understand. Next, let's move the two functions related to permissions into this new interface. For the original interface, let's also rename it to better reflect its purpose. Okay, so let's change it to something like User Fetcher Interface. While it may not be the most ideal name, it works for now. And of course, don't forget to update any references to this renamed interface. Now, we can safely remove the two permissions-related functions from the user controller class and move them to their own dedicated class. Let's call it User Permission Service, which will implement the User Permission Manager Interface contract. That's quite a mouthful. Inside the service class, we can move the two functions related to permissions. I'll quickly add some comments here. Grant permission logic goes here, and revoke permissions logic goes here. So using this approach adheres to the rules of the interface segregation principle. It's not a particularly difficult concept actually. According to ISP, you should avoid forcing classes to implement functionalities they don't actually need. That is the key there. In essence, the interface segregation principle is about splitting large interfaces into smaller, related ones. Instead of cramming many unrelated functions into a single interface and forcing a class to implement methods it doesn't need, like we saw earlier, where we ended up returning null, we create more focused, meaningful interfaces. This keeps the code clean and adheres to best practices. Okay, now let's move on to the last principle in Solid, dependency inversion. Okay, so we're at the last principle of Solid, the dependency inversion. So what does this principle teach us? The dependency inversion principle, or DIP, states that high-level modules, like the controllers or service classes, should not depend on low-level modules. Instead, both should depend on abstractions, the interfaces. Well, think of DIP as a fancy way of saying, don't lock yourself into a specific implementation. Instead of having your core logic, that high-level code in your controllers, depend directly on some classes, you make them both depend on an interface. That way, you can swap out those services whenever you want, and your controller code stays nice and clean. So by depending on an interface, your controller or service class doesn't need to know any of the details about how the concrete class or that low-level modules does its work. Let me give you a quick demonstration of this concept. Imagine you have an online payment controller where you process a payment. This Stripe payment gateway class is the low-level module, okay? And the controller itself is the high-level module. Remember the rule of dependency inversion. High-level modules, like controllers or service classes, should not depend on the low-level modules. Instead, both should depend on abstractions, okay, the interfaces. If I inject the concrete class for Stripe directly into my controller, now I am locked into that setup. My high-level module now depends on the low-level module. If someday the requirements change, for example, the app you're building needs to replace Stripe with something like PayPal, for example, it becomes much harder to switch because our controller depends directly on the Stripe payment gateway class. This means you would need to rewrite the entire logic to switch payment processors, which is not very ideal. But if I make an interface, like, for example, payment gateway interface, we will do that later, and let Stripe or PayPal just implement that, then my controller doesn't care who's processing the payment, as long as it follows the rules in that interface. Okay, so let's do that now. Actually, first let's test this in the browser, because later on I want to show you how we can bind the interface to the payment gateway we want to use via Laravel service provider. In my web route, I'll add another endpoint here. So of course, in the real world, you won't typically make this as a post request, but for this example, let's use a GET request to see the response in the browser. The endpoint will be process payment. The controller is online payment controller, and I'll specify the function for it. Now let's go to the browser and hit that endpoint. As you can see, we got the response, paid using Stripe. Great, that works. So let's go back to the controller. This is the response we returned from that endpoint. Okay, now let's fix this. Let's start by creating an interface or contract in the contracts directory. Let's name it Payment Gateway Interface. Add the namespace, then declare the interface itself. This interface should have, for now, one function. Let's call it charge. This function will accept an amount. Okay, the interface is done. Now, back in the controller. Let's make the Stripe Payment Gateway class implement that contract. Inside the function, okay, there's nothing to change here for now. Next, in the controller itself, remember the controller is the high-level module here, right? So it should depend on the abstraction or the interface. So let's change this to Payment Gateway Interface. Then inject the interface into our constructor. Let's change this to Payment Gateway and replace the instantiation of Stripe with the Payment Gateway Interface. Also, this is no longer the Stripe Gateway because it now depends on the Payment Gateway Interface. Okay, that looks good. So now the high-level module, which is the controller, no longer depends on the low-level module, which is the Stripe Payment Gateway class. Instead, it now depends on the abstraction, okay, the interface. So now if we test this in the browser, okay, we will get an error like this, saying that the Payment Gateway Interface is not instantiable. The reason for this is that Laravel's container cannot create an object from an interface alone, because an interface is just a contract and does not have an actual implementation. To fix this, we have to tell Laravel which concrete class should be used when it encounters that interface. To do this, we must bind the interface to a concrete class, so Laravel knows how to resolve it. Let's go to the app service provider, and under the register function, we can bind the interface to a class, like this. This will accept the interface and the class as parameters. Save the changes and check it again in the browser. And there you go. It's working again, and we receive the proper response. Now imagine this. In the future, if you decide to use another payment provider, such as PayPal, for example, all you need to do is to create a PayPal class implementing that contract and register it in place of Stripe. So let's try that now. Back in the controller, I'll just copy this and change it to PayPal Payment Gateway. Let's update the message so we can see that it actually works. Change this from Stripe to PayPal. So now we have two possible implementations, one for Stripe and one for PayPal. To switch from one payment processor to another, we only need to register it in the service container. You don't have to change a single line of code in your controller. So let's register this in the service container. Okay, instead of Stripe, change it to the PayPal class we just created. Just make sure it is imported at the top. And actually, that's all you need to do to switch implementations. Let's go back to the browser and try this. Refresh the page. And as you can see, the message has changed. We are now using the PayPal Payment Gateway. That's how easy it is by simply binding the interface to the class here. Back in the controller, let me just fold this code. Again, this controller, remember, is our high-level module. And these two are the low-level modules. Okay, always remember that dependency inversion means that the high-level module, like our payment controller, depends on the abstraction or interface. It decides what needs to happen, example, process a payment, but doesn't need to know how it actually happens at a low level. The concrete class, or the low-level modules, something like the Stripe Payment Gateway or the PayPal Payment Gateway classes, it manages the intricate implementation details of interacting with external APIs. This captures the core idea of the dependency inversion principle. Using this technique, it becomes very easy to switch to a different implementation, as you have seen in our app service provider. By simply switching the class to something else, everything still works without changing a single line of code in the controller itself. This allows you to switch implementations at will if you ever find yourself in a situation where your project requires a different kinds of dependencies. Okay, so we have now reached the end of this video. Thanks for tuning in, and I hope you gain a better understanding of the solid principles and how they can improve your code. I understand that grasping all these concepts at once might be a bit challenging, and that is okay. Applying them in the real-world scenarios isn't always as straightforward as the simple examples I've shown here. But I hope this gives you a good starting point for writing cleaner and more efficient code. Okay, that's it guys. Thank you for watching.